Let's get started. We do have an exam on Wednesday because it's just over the vibrational stuff, and then we'll do some atomic orbitals and atomic spectroscopy, and we'll have an exam over that, and then we'll finish up the semester with MO theory, molecular orbital theory, where those atomic orbitals are then used in molecules, and that's probably the most challenging topic that we cover. So we get into crazy looking orbitals and so on. But today I'm going to go through this pretty quick because this would be sort of just that added little extra on the vibrational spectra that you might run across. We'll hit a few of the symmetry exercises to show that overtones and combinations are allowed, but then we'll get done about halfway through so that you have some time for questions to get ready for the exam. So we're talking about vibrational combination bands and overtones. Most of the spectra, the peaks that you see in an infrared spectrum, are fundamentals. So what are the quantum numbers associated for a vibrational fundamental? Because remember, every peak you see in a spectrum is a difference in energy levels. So it involves two quantum numbers. So which two quantum numbers are used for a fundamental in vibrational spectroscopy? 0 to 1. Did I hear that correctly? Yes. So 0 to 1. For the particle in a box, what was it? 1 to 2. Exactly. So in vibrational spectroscopy, you start at 0, and 0 to 1 is our fundamental transition. Combination bands are combinations of multiple fundamentals. So you might have the stretching motion go up by 1 quantum and some kind of bending motion go up in 1 quantum. So you could have a stretch and a bend. So this motion here might go up by 1 quantum in the stretching and 1 quantum in the bending. And so that would be a combination of the bending and the stretching. Today we're going to look at the symmetries of those. You could also have overtones. So what would be the first overtone? The quantum states associated with the first overtone in vibration. 0 to 2, so it's jumping by 2. And then the second overtone is 0 to 3, so it jumps by 3 levels. So those are overtones. And we would also want to look at the symmetry associated with those. So here's the spectrum of automobile exhaust. This is a little bit of review, so I'll go through quickly. So here's our mid-infrared spectrum. Over here we have CO2, the bending motion. We have the stretching motion in CO2. That's the asymmetric stretch, which is infrared active. And then we have a Raman active stretch that doesn't show up in the infrared. We have the water bending motion. This lump here is the water stretching motion. And then we have these two fuzzy peaks. These are gas phase peaks, and those end up being combination bands. And so we're going to look at these really quickly. So these are the vibrational motions in CO2, 2 of them. The asymmetric stretch is on top. You see that it's asymmetric. The bonds are stretching and out of phase with each other, and the bottom one is the symmetric stretch. Both bonds stretch together, both bonds compress together. The symmetric stretch is Raman active. The asymmetric stretch is IR active. What about this bend? This bending motion is IR active. And so we could see these Raman modes, and then this bending motion is really low in energy. So this is the bending motion, and it's that second quantum state, nu2. Well, we can combine this one with the Raman mode and make an infrared active motion. We can have an overtone of this bending motion coupled with the Raman motion. Let's see, no, it's coupled with the IR, the asymmetric stretch. And make this 3684 peak. So these are the quantum states that we have, and these are the symmetries associated with them. So you can see that we start out in the ground states for all 3, and those are all top row symmetry. We have Z-polarized light, which is A1U. See that right here. And then we have the upper state, nu3 is A1U. We have 2 times the bending motion, which is E1U, and then nothing happens to the third vibrational frequency. So it's still in the ground state, A1G. So lots of things are happening in these combination bands. And we could work through the symmetries and show that these are allowed. So here's the support for the combination band in CO2. So we have top row times top row times top row, and anything times the top row is unchanged. That's what the little guy was doing in the first meet. Okay, so that's all A1G. Then anything times A1G is unchanged. So this is A1U. A1U times A1U. A1 times A1 is A1. And U times U is G. Is everybody comfortable with that? U times U is G. Good. So then we get E1U times A1G. Again, A1G is top row, so nothing happens to E1U. Here's where it gets interesting. E1 times E1 is equal to A1 plus A2 plus E1. So this is from that character table, and then the U times U gives us G's. And then A1G times all three of those pieces, nothing is changed by that. And so this is why when I say at the end, when you get down and there's no more multiplications, if the integrand, the thing that's being integrated, contains the top row, then it's not zero. So the top row is A1G, it's in that sum somewhere. And so since we have an A1G term in that sum, then this integral is not equal to zero. And so we have the possibility of this combination band showing up in the infrared. Now, the sad part of using symmetry is we don't know how strong it will be, but it is allowed. And so this is support for that band being assigned the way it is. We're going to do a bunch more. So it's really just to show you how these things, this is as complicated as it gets. We have all of these symmetries multiplied by each other, and we just do them one at a time. So let's look at the normal modes and frequencies of acetonitrile. So look at all of these fundamentals. We see all of these peaks. They're present in both the Raman and the IR. Okay. So the Raman is down here in the dotted lines, the IRs and the black lines. We have the stick spectra from Gaussian stuck in there. And we see some combinations. So we see this combination band, nu3 plus nu4. And we see this combination here, nu7 plus nu8. And then over here we have the overtone of nu8. So the 2 nu8 is over here. So let's look at some of these. So here's the nu3 plus nu4 combination band. This is the easiest one because it's all A1. It's all top row all the way across. So we could just do this. Boom, 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 boom. We've got A1 all the way down. That's super easy. But let's look at the nu7 and nu8. This one, we have, again, we start in the ground state for nu7, the ground state for nu8. This combination band is really just one quantum excited in each of those. So it goes to 1 for each of those. And then we're going to use Z polarized light. So we end up with A1, A1 again. E times A1 is E, and then we have E times E. So we go again to that direct product table. We see E times E, A1 plus A2 plus E. There's no G's and U's in this molecule. Why? It's a review question. We only get G's and U's with one condition. Let's back up. How many symmetry elements are there? So we have symmetry elements like a rotation axis, a reflection plane. What are they called? Let's name them off. These are the columns in the character table. So let's name off the types of columns we might have. There's symmetry elements that we use to manipulate the molecule. The first one's easy. It's E. You do nothing to the molecule. It's the identity. What are the other four? What's that? Be bold. The XY plane is it could be a symmetry element. What would be the symmetry element that would correspond to an XY plane? What's the name of that? Sigma. Yeah, what does sigma mean? What is it? What kind of thing is it? Rotation, reflection, inversion, improper rotation. What are these kinds of things that we're talking about? Those are the symmetry elements. Yeah, the things that you do to the molecule to see if it's unchanged. So rotation is one. You could have a C2 like in water. You could have a C3 like in ammonia. But those are symmetry elements. The C part, the rotation, is a symmetry element. sigma plane. Whoever said that was good. Sigma plane. A reflection. It's a reflection. Then you have the combination of those two. Improper rotation is a rotation and a reflection combined into one symmetry element. But the one I'm looking for G's and U's is I. What is I? Inversion center. So the inversion center is what gives you G's and U's. So if the molecule doesn't have an inversion center, it won't have G's and U's in any of its little A1s, A2s, and stuff like that. So benzene has an inversion center, so it has A1G and so on. CO2. CO2 has an oxygen on both sides. The carbon's right on the middle. So the carbon is sitting on the inversion center. The oxygens can invert into each other. So that's why CO2 had G's and U's. Acetonitrile? No, we have a nitrile on top and a methyl on bottom. And so there's no inversion center. So we don't have G's and U's. So that's why when we're doing this, we don't see G's and U's in the character table. Yes.
So you said
Yeah, so we would go through and look at those motions. That came from this table up here, right here. So these different motions, and so 7 and 8 were E. Yeah, and you can see them here. They're labeled with the little symmetries. Yeah, that's a good question. So we went through this one, and then we got the 7 and 8 E's. We get down to E times E. We use the direct product table, but now you've seen that enough times that you should say, okay, E times E is A1 plus A2 plus E. Okay. And then if we had G's and U's, we would use the G and U symmetry on that, on top of that. So this gives us A1 plus A2 plus E, and A1 is the top row of our C3V character table. So this is not equal to 0. Okay, so let's do the, let's see, we just did 7 and 8. Something happened. Okay. Oh no, this is with XY light, sorry. So this is 7 and 8. Let's see if XY light is allowed. So XY light is E. So we have A1 times A1 is A1, A1 times E is E. So now we have 3 E's times each other. So what do we do in that situation? Well, the first 2 E's produce an A1, an A2, and an E. And then E times A1 is going to give us E. E times A2 is going to give us E. We can see that. So E times A1 is E. E times A2 is E. E times E is the whole 3 things here. So we're going to get A1 plus A2 plus 3 E's. You see that? So that's what we end up with in the next step. But we see that A1, which is top row of the character table, so this is not equal to 0. So this combination band is allowed with XY polarized light or with Z polarized light. And so now we can, that's pretty much it for the combination bands. I'm just showing you that they might show up if there's symmetry allowed. We don't know how intense they are, but we can get Gaussian to do that now. So Gaussian has an anharmonicity keyword, I guess you could put into a Gaussian calculation. It really extends the time that it takes to do the frequency calculation, but it will calculate the intensities of all the combination and overtone bands, and there's a crazy amount of them. So anyway, that's something that you could do in Gaussian, and you may do in the future if you get into science and infrared spectroscopy. Okay. So let's go to the questions on the homeworks. Get ready for the test. I'm gonna break the video here and then restart it, so there'll just be a review video that y'all can look at.